The article, "Every Terrifying Type of Black Hole Explained," serves as a captivating primer on one of astronomy's most enigmatic subjects, framing black holes not merely as destructive voids, but as multifaceted cosmic phenomena. In this first part of our analysis, we delve into the contents treatment of the three most observationally grounded categories: stellar, intermediate, and supermassive black holes. These form the empirical backbone of the piece, drawing on decades of astronomical data to illustrate how black holes transition from stellar remnants to galactic anchors. By examining the strengths in explanatory clarity, the integration of real-world examples, and potential oversimplifications, we can appreciate how the article bridges layperson curiosity with scientific rigor, while also highlighting beginning with stellar black holes. The content excels in demystifying their formation and detection, portraying them as the small seeds of the black hole hierarchy. The description of a massive star's collapse, requiring at least 20 solar masses into an object no larger than a single city, is both accurate and evocative, leveraging analogies like compressing the Himalayas into a pebble to convey extreme density. This approach aligns with established astrophysics. Core collapse supernova indeed produce black holes in the 3 to 100 solar mass range, as confirmed by observations from facilities like the Chandra X-ray Observatory. The article's emphasis on detection methods such as X-ray emissions from accretion disks and gravitational wave signals from mergers via LIGO, Virgo, is a highlight. For instance, referencing Cygnus X1, discovered in the 1960s and weighing about 21 solar masses, not only grounds the narrative in history, but also nods to cultural anecdotes like Stephen Hawking's Lost Bet, adding a human element that enhances engagement without sacrificing facts. However, the content's portrayal of stellar black holes as cosmic ghosts drifting silently through the Milky Way, potentially numbering in the millions, touches on a point of mild controversy. While estimates from population synthesis models suggest 10 to the power of 8 to 10 to the power of 9 such objects in our galaxy, the article underplays ongoing debates about their distribution and merger rates. Recent LIGO detections have revealed unexpected masses. For example, the 85 solar mass black hole in GW 190521, challenging traditional stellar evolution models and suggesting alternative formation channels like hierarchical mergers in dense clusters. By not delving into these, the piece risks presenting a static view, though this may be intentional for accessibility. Transitioning to intermediate black holes, the article positions them as the missing link in black hole evolution, weighing hundreds to thousands of solar masses. This is a strong point, as it addresses a genuine puzzle in astrophysics: how stellar black holes grow into supermassive ones. The content's discussion of candidates like the 1 in 47 Tucanae, or HLX-1, around 20,000 solar masses, is well supported by evidence from globular cluster dynamics and X-ray bursts, reflecting research from telescopes like Hubble and NuSTAR. By highlighting their elusiveness due to faint signals and rare feeding events, the narrative builds suspense, mirroring the scientific community's excitement over potential detections via future gravitational wave observatories like LISA. Yet this section also encapsulates one of the article's more controversial elements: the rarity and even existence of intermediate black holes. While the content suggests they must exist, the evidence remains circumstantial, with many candidates debated. For example, HLX-1 might be a background active galactic nucleus. Critics in the field argue that intermediate black holes may form rarely, perhaps only in specific environments like nuclear star clusters. And alternative theories propose rapid growth via gas accretion without an intermediate phase. The article's optimistic tone could be seen as overstating consensus, but it effectively uses this uncertainty to underscore black holes' mysterious nature, turning a potential weakness into an educational hook. Finally, the supermassive black hole segment stands out as the article's empirical pinnacle, describing them as titans at galactic centers with masses in the millions to billions of solar masses. Examples like Sagittarius A star, 4 million solar masses, and M87's 6.5 billion solar mass behemoth are spot on, bolstered by the 2019 Event Horizon Telescope image, a landmark achievement that the content celebrates aptly. The explanation of their role in galaxy evolution via quasar feedback regulating star formation draws from well-established models like those in simulations from the Illustris project. This ties black holes to cosmology, showing their influence beyond mere gravity, which is a masterful way to elevate the discussion. Controversially, the origins of supermassive black holes remain unresolved, and the article presents theories like mergers or direct collapse without favoring one, which is balanced but could frustrate readers seeking resolution. Debates rage over early universe growth rates. JWST observations of massive black holes at high redshifts suggest they formed quicker than models predict, possibly via primordial seeds, foreshadowing later sections. Overall, this part's strength lies in its seamless integration of observation and implication, making abstract scales tangible while inviting deeper inquiry. In summary, the observational categories in the article provide a solid foundation, blending education with wonder. They highlight black holes' detectability through indirect means, but controversies around formation and detection underscore the field's dynamism. Shifting from the observable to the speculative, the second part of our analysis examines the article's handling of primordial and quantum black holes, which occupy the more theoretical end of the spectrum. These categories push the boundaries of current physics, blending cosmology with quantum mechanics and challenging readers to grapple with unproven ideas. The content's strength here lies in its ability to make abstract concepts accessible through vivid imagery and real scientific puzzles, such as dark matter and the unification of theories. However, this is also where controversies intensify, as the article navigates hypotheses with varying degrees of empirical support. By dissecting the explanatory techniques, evidential basis, and debated implications, we uncover how the piece balances wonder with caution, while highlighting potential pitfalls in presenting speculation as near certainty. Primordial black holes are introduced as ancient relics from the universe's infancy, potentially forming in the chaotic moments post-Big Bang through density fluctuations. The article's narrative framing them as older than any star and possibly as small as atoms, yet heavier than mountains, is a compelling hook, drawing on theories from physicists like Stephen Hawking and Bernard Carr. This aligns with cosmological models, where quantum fluctuations in the inflationary epoch could seed such collapses, producing primordial black holes across a vast mass range, from micrograms to asteroid scales. The content smartly ties this to unsolved mysteries, positing primordial black holes as candidates for dark matter, which accounts for about 85% of the universe's mass based on galactic rotation curves and cosmic microwave background data. By suggesting trillions might pass through our solar system undetected, the piece evokes a sense of hidden ubiquity, enhancing the terrifying allure promised in the title. A key strength is the article's linkage of primordial black holes to broader cosmic evolution, such as accelerating the growth of supermassive black holes in the early universe. Observations from the James Webb Space Telescope have indeed revealed quasars powered by billion solar mass black holes within the first billion years post-Big Bang, defying standard growth timelines from stellar seeds alone. Primordial black holes, as head starts, offer a plausible solution, supported by simulations in papers from journals like the Astrophysical Journal. Detection methods mentioned: microlensing events distorting starlight or Hawking radiation bursts, are accurate, reflecting ongoing searches by experiments like the Fermi Gamma-Ray Space Telescope, which hunts for evaporation signatures from low-mass primordial black holes. Yet this section harbors significant controversy, as the dark matter hypothesis for primordial black holes is far from settled. The article's enthusiastic tone, if true, that would mean the missing mass of the universe is literally made of invisible black holes, might overstate viability given stringent constraints. For instance, microlensing surveys by Macho and Ogle have ruled out primordial black holes in certain mass windows. For example, 10 to the -7 to 10 solar masses, comprising all dark matter, while LIGO's merger rates imply limits on others. Feminist critiques in cosmology aside, the debate centers on whether primordial black holes could evade these bounds through clustered distributions or non-standard formation. By not addressing counter-arguments, like the preference for particle-based dark matter, for example, WIMPs or axions, in models like Lambda CDM, the content risks simplifying a polarized field. Nonetheless, it effectively uses primordial black holes to bridge quantum and cosmic scales, portraying them as fossils from the very birth of the universe, which inspires without outright misleading. Moving to quantum black holes, the article ventures into the Planck scale realm, where general relativity and quantum mechanics intersect uneasily, describing them as smaller than an atom, yet embodying the clash of theories, is apt. Referencing the Planck length, 10 to the power of -35 meters, as the quantum gravity threshold. The inclusion of Hawking radiation, where virtual particle pairs near the event horizon lead to evaporation, is a clear, non-technical explanation of a profound idea from Hawking's 1974 paper. For minuscule black holes, this process would be explosive and instantaneous, contrasting with the eons required for larger ones. As the content notes, the speculative allure is amplified by potential origins in the early universe or particle colliders like the LHC. Though the article correctly states no evidence exists, this ties into the quest for a theory of everything, such as string theory or loop quantum gravity, where quantum black holes could test resolutions to singularities. The piece's restraint in labeling them highly theoretical is commendable, avoiding hype seen in some popular science writing. Controversially, the existence of stable quantum black holes is dubious. Most models predict they evaporate too quickly to observe, and LHC searches, for example, for microscopic black holes in extra dimensions, have yielded null results, as per CERN reports. Debates rage over whether quantum effects prevent singularity formation altogether, with alternatives like fuzzballs in string theory challenging classical notions. The article's portrayal as a thought experiment mitigates this, but could elaborate on why unification remains elusive, perhaps referencing the information paradox, resolved, or not, by recent holographic proposals. Incorporating the bonus round, binary black holes, white holes, and wormholes adds flair, with LIGO's 2015 detection of mergers validating Einstein's waves. White holes, as expellers of matter, are purely hypothetical, often dismissed as thermodynamically unstable, yet the content uses them playfully to spark imagination. Overall, this part transforms theory into narrative adventure. But controversies underscore the need for balanced skepticism. It elevates black holes from destroyers to probes of fundamental reality, setting up a holistic view. In this final part of our analysis, we synthesize the article's overarching structure, evaluate its cumulative impact on readers, and critically assess its strengths, alongside the most contentious elements. Every terrifying type of black hole explained masterfully escalates from empirical observations to speculative frontiers, culminating in a reflective bonus section that ties everything together. By framing black holes as a hierarchy across 5 levels, plus extras, the piece not only educates, but also inspires awe, positioning these phenomena as gateways to cosmic understanding. This holistic approach reveals the article's core achievement, transforming dense astrophysics into an engaging narrative that appeals to both novices and enthusiasts. However, it also amplifies controversies, particularly in blending fact with hypothesis, which we unpack here to gauge its broader implications for popular science communication. Structurally, the article's progression is one of its greatest strengths. It begins with foundational concepts like event horizons and accretion disks, building reader confidence before ascending to increasingly abstract territories. The stellar to supermassive arc grounds the discussion in verifiable science, while primordial and quantum sections venture into theory, mirroring the field's own evolution. The bonus round on binary mergers, white holes and wormholes adds a playful coda, acknowledging black holes' role in thought experiments. This escalation culminates in a provocative question. Which type of black hole shocked you the most? Fostering interaction and leaving readers pondering origins and quantum enigmas. Vivid analogies, for example, black holes as cosmic trapdoors, and real examples, LIGO detections, EHT images, enhance accessibility, making complex ideas like Hawking radiation digestible without dumbing down. The educational impact is profound, demystifying black holes' terrifying reputation by emphasizing they're not roaming vacuums, but natural outcomes of extreme physics. By linking them to galaxy formation, dark matter, and quantum gravity, the content underscores their interdisciplinary relevance, potentially sparking interest in STEM. Its up-to-date references, JWST insights, recent mergers, ensure timeliness, while avoiding jargon overload keeps it inclusive. Yet this blend of wonder and science invites criticism, particularly in controversial areas. The portrayal of intermediate black holes as essential missing links is debatable. While candidates like HLX-1 exist, many astronomers question their prevalence, favoring models where supermassive black holes form via direct collapse or rapid accretion, bypassing intermediates. This optimism might mislead readers on consensus, especially amid ongoing debates fueled by LISA's anticipated data. More polarizing is the speculation on primordial black holes as dark matter. The article's thrilling suggestion that they could be trillions passing through us captures imagination, but overlooks evidential hurdles. Constraints from microlensing, for example, Subaru HSC surveys, and CNB distortions limit primordial black holes to narrow mass ranges, and particle candidates like axions remain favored. By not addressing these, the piece risks hype, a common pitfall in pop science that could erode trust if future evidence contradicts. Quantum black holes and bonuses amplify this. White holes, dismissed by most as unphysical due to entropy violations, border on sci-fi, potentially blurring lines for lay audiences. While labeled speculative, their inclusion without deeper caveats might confuse theory with fact. Overall, the article's strengths, engaging storytelling, comprehensive scope, and inspirational tone outweigh controversies, making it a valuable resource. It reminds us, black holes aren't just destroyers, but probes of reality's limits. For science communicators, it exemplifies balancing excitement with accuracy, though tighter scrutiny of debates could enhance credibility. In an era of misinformation, such pieces foster curiosity, but must navigate speculation carefully to truly enlighten.